Okay, hello everybody, let's get started. My name's Julian Hyde. I work for Hortonworks, and I'll be talking, and thanks for coming, by the way. I'm the original author of Calcite. I work for Hortonworks. I'm involved in several things, but most of it is centered around the ideas of query optimization, query planning, that kind of stuff. My Twitter handle is Julian Hyde, so if you want slides of this, I'll be posting the slides to Twitter right after this talk. So that's an easy way to get hold of the slides. So what am I talking about today? I'll give a brief introduction to Apache Calcite, but I'm focusing particularly on data profiling, which is several reasons why it's interesting. First of all, it kind of gives you an idea of some of the challenges that we're facing in query optimization. It also does what I like to call data optimization, which is if you want your queries to run faster, the solution may not just be at planning time, it may also be in terms of how you organize your data. And so we are looking at ways of helping you organize your data so that it can be queried more efficiently. The other thing is just the nerd in me, this is a very interesting algorithm. It's a very difficult problem. It's a big data problem that we needed to solve in order to do good query optimization. So it's just interesting seeing the evolution of a difficult algorithm and some of the techniques that are used to solve the problem. And so, we'll go into kind of new techniques like data sketches, which we use to help solve this problem. And then looking at how this data profiling algorithm can be applied to some other problems, not just the motivating problem. Okay, so quick introduction to Apache Calcite. First of all, who's heard of Apache Calcite? Okay, good. Not a lot of people have heard of it because it's not a product as such. Even though I work for Hortonworks, you can't call up Hortonworks and get support on Calcite. It's an enabling technology inside a lot of big data technologies. It powers Hive's cost-based optimizer, for example. It's also in Drill. It's being increasingly used in a lot of the stream processing Apache projects. Are experimentally adding streaming SQL to support, and Calcite is helping define what streaming SQL would look like and defining the engine that's making that possible. And there are, some for-profit companies that are using it. What is Apache Calcite? You can think of it as a database that doesn't own any of its own data. Or you can think of another way of thinking of it is it's a kind of a toolkit for building a database. But it's not a database itself. And the area it focuses on is relational algebra. So the abstract representation of queries that SQL is translated into relational algebra, which is a mathematically pure representation of a query that can then be manipulated, and you can apply transformation rules to optimize it or to otherwise just understand it. And this relational algebra, as we'll see later, is good for not just query optimization, but other things like data optimization. It's a Java library. It embeds very easily. There's nothing to install. You just include a jar or one or two jars inside your project. And the other thing about it is it doesn't have, because it's not a product, it doesn't have a huge audience. Our main community are developers, people that are writing databases. But it's still cool technology to learn about. Okay, so quick 2 slides about the core of what Calcite does. Top right corner of the screen is a SQL query. That it joins 2 tables, a table in Splunk and a table in MySQL. So it's a federated join. And the first thing Calcite does is it parses it and converts it to relational algebra. So this relational algebra, the data's you think of the data kind of flowing from left to right. And each of these ellipses is a logical operator. So data flows out of Splunk and MySQL. It goes through a join, then goes through a filter, which is a where clause, a group by operation, and a sort, which represents the order by clause. So this, produces the same result as this SQL. The challenge that Calcite does is how do we optimize that? How do we convert this query plan into something that produces the correct result, but does it as efficiently as possible? And the trick that Calcite uses, and all main commercial DBMS optimizers use, is to apply query transformation rules. So if you watch the diagram, we can push the filter through the join and into Splunk. And so Calcite, this is just an example of applying two rules, which is you can push a filter into a join if the filter is only using columns from that side of the join. And then you can push the filter down to the data source if the data source is able to execute filters. So that's two rules being fired. In Calcite, there are probably 100 or more rules defined, and then you can add your own. And Calcite is a framework that will basically apply all of the rules that it can in order to transform your query into something that has a low cost. And these rules, each individual rule is difficult to write correctly. Even that rule that pushes a filter through a join, was probably several weeks of development effort. But once they're working, they stay working, and then people can just kind of assemble sets of rules for particular tasks. It might be query optimization, but it might be, you might use it for other kinds of purposes. Okay, so here's just, this is a kind of a back of the envelope calculation. You'll notice everything is a power of 10. So just to give you a feel of the kind of problems, let's just suppose you've got a 10 terabyte database and a disk that can read data at 10 gigabytes per second. And your query needs to read a terabyte of data. If you just do the math, it's just going to take 1,000. It's impossible to execute this query in less than 1,000 seconds because you just can't get the data off disk any faster than that. So if we want to answer that query in 1 second, we have to cheat, right? There's just no way of the laws of physics just prevent us from executing the query any faster than that. And so here are some of the tricks that people will use. Is parallelize the query. So if you store the data on 100 disks on 25 machines, you can read the data in parallel. So the query now takes about 10 seconds. You can keep the data in memory if you have enough memory to store. If you have 10 terabytes of memory, you can basically answer the query, much, much faster. One of the problems with caching is your cache may get flushed, so the second query runs really fast, but the third query half an hour later might be, back to the original. It might be much slower because the data's being moved out of cache. Materialization is the kind of the most effective trick to do this. If you somehow know that this query is going to be asked and you pre-compute the results of this query, you can give the answer basically instantaneously. So when I talk about optimizing your data, that's one of the main tricks is to materialize the data, or perhaps materialize a summary of the data, so you can read much less data but still get the right result. And then the problem with materialization is you have to know what queries are going to be asked, or you have to have a good guess about what queries are going to be asked. So this doesn't deal with things like adaptive, changing workloads. So the optimal solution is probably some combination of materialization, caching. In other words, if someone has just read a piece of data 5 minutes ago, there's a very good chance they're going to read it again in the next half an hour. And then adapt. So spot that people are querying this, this 3-year-old data set that no one has looked at before, but maybe we need to build some summary tables on top of this data because all of a sudden, for a period of time, people are interested in it. So in order to do these kinds of, materialized view is kind of a standard fixture in databases such as Oracle and SQL Server and DB2. And so a materialized view, despite its name, is a table that contains the results of a query. And the optimizer knows that relationship between the table and the query. And so you don't have to reference emp summary in your query. You can write your query on emp. And if you're grouping by depno or something like that, then the optimizer will figure out that the query can be rewritten to use that materialized view. But there's a lot of challenges that need to be implemented in the system in order to get materialized views to work. Like, for example, you could just ask your DBA to define the materialized views, but it's a very error-prone operation. So ideally, the system would be designing these materializations. Then you need to populate them with data, and incrementally populate them as the data changes. Then when they're populated, if you know they're valid, you need to rewrite the queries to use those materializations, making sure you're doing it safely. You're not introducing any errors because you've misapplied the rewrite rules. And then you should be adapting and creating new materializations based on the workload that you're seeing. So long list of challenges in order to get in order to achieve this kind of cliff notes of data, using materializations to answer queries. Today I'm really focusing on how we design materializations. That's the motivating example that's driving this here. So when we look at a data set, a star schema or something like that, how we understand what possible summary tables could be created, the size of those summary tables is crucial. And if we're, for example, creating a summary table which contains all combinations of years and zip codes, then it's going to have five distinct years, 43,000 distinct zip codes. It's going to have approximately 5 times 43,000 rows in it. So we need to understand what the size of these summary tables is going to be before we go and create them. And the goal is that for any given query, with any particular group by clause, we will hit a summary table which is, first of all, exists and is valid, but is significantly smaller than the raw data set. So in this kind of simple example, another power of 10, we're assuming we've got 1 million rows, and we're looking at the sizes of all these possible summary tables. One interesting thing here is, so most of the things are independent, right? So you've got 12 distinct values for month, you've got 5 distinct values for year, and sure enough, there are 60 distinct values for year and month combined. Likewise, there are 2 distinct values for gender, therefore 10 distinct gender and year combinations. Zip code and state are kind of interesting because there are 50 distinct states and 43,000 zip codes, but there are only 43,400 combinations of zip code and state. Because these are almost functionally independent, there are very few zip codes that cross state boundaries. So the implication of this is it'd be crazy to create a summary table on zip code. It'd be much better to create a summary table on zip code and state because it only has a few more rows. But we can still, we can answer queries that are grouped by state and answer queries which is grouped by zip code. So that is a valuable summary table to create. We'd like the system to be able to figure this out. So, so there's a well-established algorithm. It's about 20 years old to design summary tables. And I'm again, just a kind of a random example. Suppose we have a database that has 30 columns, in other words, 30 attributes that we could aggregate by, and 10 million rows in your database. you want to find the summary tables that take, you have a certain budget of disk space, you want to find the summary tables that can answer your expected workload the most. So the algorithm is basically create a combination of summary tables, or assume you have a particular set of summary tables, find the one summary table you could add which will give the most incremental benefit. So which is able to, in other words, answer queries that couldn't have been answered with the existing set of summary tables and doesn't use a lot of extra disk space. So this algorithm works fairly effectively. The problem is this algorithm keeps on asking hard questions because it's examining the whole space of possible summary tables. And if you have 30 columns, that's 2 to the 30 possible summary tables. Each combination of attributes, X, Y, Z, is a possible summary table. So this algorithm asks a lot of questions, and each of those queries is basically a count distinct. And potentially that's a full table scan. It's a very complicated question to ask. And this algorithm produces 2 to the 30 of these queries. So, and by the way, when we run this algorithm, it produces a result something like this. So each of these orange ellipses are the ones that the algorithm has decided are optimal. In other words, these are the summary tables it's going to materialize. This one is not materialized because from these results, from these 10 rows, we can roll up to this. And if you look from the top to the bottom, virtually any path you take from the top to the bottom, you're going to hit an orange ellipse with a relatively small number of rows in it. So that's what we're trying to achieve, but we need to produce the stats that are going to power this algorithm. So, so data profiling is basically computing or giving us these statistics that are necessary to power this algorithm. And it turns out when you have these statistics, there's other things, a lot of other things you can do with this data. Not just power this relatively esoteric algorithm to design summary tables. So a naive way of solving this is let's just compute each combination. Let's execute 2 to the power of 30 select count distinct queries. Okay, that's going to take a while, even on a high performance database. We can use sketches. Sketches are a relatively new technique. They kind of came of age about in the last 10 years. They're a way of producing approximate results, but still very, very, very close approximations to the actual result using a very small amount of memory. So there's one of the most popular sketches is called hyperlog-log, and it takes 1.5K of memory, and it can produce a result which is within 2% of the exact answer. And then it turns out, the sketch-based approach helps, but it still doesn't achieve what we want. So we have to use some other techniques like using parallelism and using information theory. So I'll get to that shortly. First of all, sketches. So here's a graph of hyperlog-log and the relative error. So along the baseline is the cardinality of the data. So 1 distinct value, 10 distinct values, 100 distinct values. It turns out even if you've got 1 million distinct values, then the relative error here is it's basically all somewhere between 1% and 2% error. And this is using basically 1.5K of working memory. So it's pretty close to magic how it can produce a really good estimate of a large of cardinality and only using a small amount of memory. So if we use this approach, rather than having to do 2 to the 30 passes over the data, we can compute, if we have 16 megabytes of memory, we can compute 10,000 sketches. In other words, in parallel, each time we make a pass over the data. So we can compute the count distinct of A and count distinct of B and count distinct of A, comma B and count distinct of A, comma B, comma C, and so forth. We can compute 10,000 of those each time we make a pass. But still, the 2 to the 30 is still, we're still down to about 10,000 passes over our data. So what next? So information theory says, if we look at, and I guess another way of looking at it is we're looking at probability, right? So if most combinations of columns are kind of statistically independent. So if we combine gender and state, because they're independent of each other, there are 100 distinct values. So if you hadn't seen the data and someone says, how many distinct values of gender and state are there? You'd say, well, 2 times 50, 100. And the answer is, well, yes, it's 100. So this is unsurprising. Now, it is surprising that, month and zip code, again, very unsurprising. The value is very, very close to what we'd expect. The value that is surprising is state and zip code. In other words, this is something that's worth storing. The algorithm takes the approach that if something is completely unsurprising or is only moderately surprising, we may compute it, but it's not worth storing it. So the actual model that we're producing from this algorithm won't even bother to store the number of gender and zip code, gender and state, or indeed gender and zip code combinations, because they don't tell us any information. So we only store the stuff that is statistically surprising. And then furthermore, we have to figure out where to go next. So because, well, is the combination of, let's see, gender, state, and zip code, is this surprising? Well, we would predict, we know the combinations of gender and state, gender and zip code, and so forth, and they have these cardinalities. So we'd estimate based on these that the cardinality is 86,799. It's actually 83,000. So again, not very surprising, which means we're probably not going to bother going any further down and adding further attributes to this. So here's the algorithm. We use surprise in 3 ways. So first of all, if something isn't surprising, we don't store it in the resulting model. Secondly, and this is a kind of an unproven hypothesis, I'd love to see a proof for it. But if a combination of attributes doesn't have a surprising cardinality, then their children, adding extra attributes isn't going to be surprising either. And lastly, if we stop seeing surprising results, then it's probably time to stop, because we're not going to, none of the descendants adding more attributes to this model isn't going to produce any extra information. So that's the algorithm we implemented. And here is kind of a trace of the process of the algorithm. So each time here we're making passes over the data and computing the results and measuring how surprising the results are. And when the first few passes, the results have a surprise of 1. In other words, they have maximum possible information, because we didn't know that state had 50 possible values. So that's a surprise of 1. Then we make some further passes, and we start finding some results here which are unsurprising. And this rising line here is the surprise threshold. In other words, when we start off, we will accept anything, even if it's not surprising at all. But as the algorithm progresses, we increase the threshold. So we now require something to be pretty surprising before we will actually do anything with it. And so at some point, we haven't implemented this kind of auto-stopping, but I think around about here, I think the algorithm should just stop and say, there's nothing particularly surprising. Let's just finish. Okay. One of the implications of this is that hierarchies are kind of an essential part of pretty much all OLAP systems. So, the first thing you do if you're designing an OLAP database is you define the time hierarchy and the product hierarchy and the customer hierarchy. And so, from this you can deduce that the phone number of a customer, the city of a customer is functionally, the state of a customer is functionally dependent on the city they live in, and so forth. And the question is, why are we doing this? It's kind of useful for the user interface to be able to double-click on a state and see the cities in it. But I would claim that what we've discovered here is that in terms of data storage, you shouldn't have to define hierarchies in order for the system to store data effectively. The system should be able to figure out for itself that this functional dependency between year, quarter, month, and date, and so forth. And furthermore, these things which are almost hierarchies, there's not a functional dependency between state and zip code and, zip code and state, but we still get a lot of benefits because they're almost functionally dependent. So if I try and define this hierarchy in an OLAP system, it would say that's not a hierarchy because this particular zip code crosses a state boundary. But from a storage perspective, it's still saving me a lot of space. So I would advocate taking hierarchies out of a lot of OLAP systems and let the system just figure out the functional dependencies. Some other applications of this stuff were obviously lots of applications in in query optimization. So join optimization is a major problem, especially if it's a really big join. If you've just joined two tables together, you have a pretty good idea of what the distributions of the values coming out of that join are. But by the time you've done a 10-way join, really all bets are off. Optimizers require statistics in order to do a good job, and after even a 5- or 6-way join, the statistics are really, really crappy because you just don't know how the data is being distorted as it's being joined. With this information, after you've done an n-way join, you can still have a pretty good idea of what the cardinalities are going to be. There's kind of motivated by that problem, there's a new benchmark called the join order benchmark, which doesn't actually run queries. It does the explain plan on queries, and it uses a real data set because it turns out that the traditional benchmarks, because they want to scale them, they're all based on synthetic data sets, and synthetic data sets tend to be statistically extremely boring. And the optimizers kind of do join cardinality estimation, and surprise, surprise, they get it exactly right because the data is very uniform. The join order benchmark is actually based on real data. It's based on an extract from the Internet Movie Database. And it discovers things like movies made by French directors tend to have French actors. So this is a cardinality, a pair of correlated attributes which are across like 3 or 4 different relationship hops. So this work here, if you were to define that Internet Movie Database as a star schema, this could find that unexpected correlation between those two values, the country that the director belongs to and the country that the actor belongs to. And another application that's crucially important in query optimization is estimating how many rows come out of a group by. And in both the MapReduce and the Spark world, you really want to know if this group by is going to produce 10 rows or 10 million rows, because this affects the number of reducers you have, and it affects the number of files that you're going to produce. So if we had better stats for that, then significant advantages in query execution times. Another application of this is if you're a consultant arriving on site at a company, you'd really like to be able to just look at the company's data and just grok it, figure out what the relationships are, because the customer may not have created primary keys and foreign keys. The data may not be normalized, right? They may have denormalized a table. This algorithm can discover those functional dependencies inside a data set. Traditional approaches to profiling, you have to kind of come up with a hypothesis that this is functionally independent on that and then test it. Whereas this is executing all hypotheses and then telling you what the interesting relationships are. I think there's applications finding problems in data quality and so forth. And I'm not an expert on machine learning, but whoops. Sorry, my phone was trying to tell me something. But if you can find that two particular variables are correlated, I have a suspicion that has some kind of predictive power to it. So, this is at an early stage. It's currently a JIRA case and a pull request. It'll go into Calcite hopefully in the next release. But there's a lot of improvements that can be made to this algorithm. We can, improve the parallelism of it. Right now, it runs in a single JVM, but it could be, the algorithm could be run in a distributed framework like Spark. Right now, it only does cardinalities, so it will tell you that, state has 50 values. Or age has 77 distinct values, but it won't tell you, for example, that 10% of your data, 25% of your population has an age less than 20, and so forth. So this is all I have. There's plenty of time for questions. So. Yes. Actually, can you wait for a microphone?
Thank you. Yeah, so when we download the HDP...
I'm sorry?
So when we download the HDP, that sandbox from Hortonworks, is this included or do we have to install separately?
This isn't even in Calcite yet. Hopefully at some point, this, I see Ashutosh sitting at the back. This may make it into Hive at some point, or it may not. Right now, it's a kind of we're discussing what's possible, looking at what's possible. Certainly in Hive, we're continually trying to strive to produce better statistics, right. But it's not on Hive's roadmap at this point.
Are you looking at improving the indexes in Hive as well?
Are we going to create indexes in Hive?
Improve, yeah.
I don't know about... there's certainly an interest in creating summary tables, materialized views in Hive, if that's what you mean by indexes. Again, I'm not sure what's on the roadmap, but it's an area that's of intense interest for us. And we do know from experience that summary tables, materialized views are. It's great to have create materialized view syntax, but people find it a lot easier to create them if the system is helping design them. So we're kind of jumping to the next problem. Not just make materialized views possible, but make it easier to design them. Yeah.
In real world, how expensive is the profiling operation? Like, is it feasible to do this on a streaming kind of data set?
I suppose it's. I believe the hyperlog sketch is composable in that way. So in principle, you could do it, but remember, you've still got, a very large number of sketches. So I would think this is an algorithm that you could fairly easily just do once over. It's not something you'd need to do continuously because the distribution of columns doesn't tend to change in real time. Once you have a month of data, you analyze it, and then the patterns within that data set are going to be the same for the next 2 or 3 months. I suppose it's possible you could analyze it and then kind of watch if this column, which previously only had 2 values, now has 20,000 distinct values. But I wouldn't really bust a gut trying to make this work continuously. Yes?
So when there's a surprise after the profiling, will it make things even worse than no profiling, or just fall back to the case when there's no profiling at all?
Can you say again?
So when there's a still surprise after the profiling,
Yeah.
and you hit it in your actual data, is it possible to make it worse than the case that when there's no profiling at all, or you just fall back to doing nothing?
Is it possible for what to make what worse?
If there's still a surprise
Yeah.
after the profiling, and you hit that case, is it possible to make it worse and not doing anything at all?
Well, I don't fully understand, but one thing is that the cardinality of if you have a pair of attributes, the cardinality of the attributes combined cannot be higher than the unsurprising estimate. So if you have 2 genders and 50 states, it's impossible for them to combine to have more than 100. They can only have fewer than 100. So I guess.
Okay, so the answer is no. I see. Okay,
Yeah.
thanks.
So the data profiling has to happen before you at the actual the optimization kicks in, or how does it? I mean, like, so for example, it decides that it has to go through this particular, combination of dimensions.
Yeah.
So all of that is decided like a pre-step. I mean, like, it has to happen before, like, the data profiling itself, or is it like while the query comes, it decides all of this actually?
Yeah, the way this might be surfaced in Hive, for example, would be just an improved analyze table command. So yeah, if you want to use the cost-based optimizer in Hive, you have to have run analyze table beforehand. Yeah. But this algorithm is something that could be used inside Hive analyze table, but it could be used in other contexts as well. Yeah.
You mentioned about kind of a current single machine implementation of this algorithm. Is it open sourced yet, or can we access it somehow?
Yes, it is. Okay. Well, it's currently in this Calcite case 1788, which there's a pull request in there. It's not yet in Calcite mainline, but it probably will make it into the next Calcite release. And so, you can play around with it. By the way, I was asked to remind you to please fill out your surveys of this talk. Now all the people who didn't like it have left. Please, please fill out your surveys of this talk in the app on your phone. And lastly, I'm going to post these slides on the Twitter account. So if you want this, they'll be published on the DataWorks Summit website, but you can get them earlier via Twitter account. That's Julian Hyde. Okay, I think that's all I have time for. If there's any more questions.